Alright, in this video we're looking at again reaction stoichiometry for grade 11 chemistry. And in this particular video we're going to look at limiting reagent problems. So this is on the reaction stoichiometry worksheet number 2 if you have it with you. We're going to do a couple of questions from there, and they're multi-part questions. If you don't have the worksheet, just pause the video as you need to and you can work the questions out yourself on a piece of loose leaf. So the first question says, when aluminum metal powder is mixed with iron oxide and heated, the following highly dangerous exothermic reaction occurs. It's called the thermite reaction. It says the final temperature gets so hot that the iron metal being produced is liquid. It actually melts the iron metal being produced. So classify the reaction and balance it. So we see here an element, aluminum, and it's reacting with an ionic compound, iron oxide. So this is, in class, we described this as two people dancing, a positive and a negative, and somebody over here looking to cut in and dance with them as well. So that we described it as a single replacement reaction. Okay, so single, oops, I just misspelled that. You get the idea, single replacement. We want to balance this. We have 3 oxygens over here in the aluminum oxide and 4 oxygens in the iron oxide. So to balance that, you think of the smallest, the lowest common multiple of 3 and 4. What number do they both go into? Would they divide into equally? And the answer is 12, right? So to get 12 oxygens, we would need to put a 3 here. 3 times 4 is 12. To get 12 oxygens, we'll need to put a 4 there. 4 times 3 is 12. So that fixed the oxygens. This 4 gives me 8 aluminums, so I'll put an 8 over here. And this 3 gives me 9 irons, so I'll put a 9 over here. So that's the balanced equation, 8, 3, 9, 4. Part B says a chemist mixed 5 grams, 5.00 grams of aluminum powder with 10.0 grams of iron oxide in a crucible. Determine which of those two reactants in this experiment is the limiting reagent. Recall that the limiting reagent is the reactant that gets used up first in the chemical reaction. When the aluminum and the iron oxide react, one of those two reactants will get used up before the other one, almost certainly. It's possible that they would both get used up at the same moment, but almost always one of them will run out before the other. For example, if you were baking some cookies at home, chocolate chip cookies, and suppose you have butter, you have flour, you have chocolate chips, you have all the different ingredients to make the cookies. But once you run out of the flour, if that's the ingredient that runs out first, you have to stop baking the cookies, even though you might have extra eggs, you might have extra chocolate chips. Once you've run out of that one ingredient, flour, you can't make any more chocolate chip cookies. So in that case, the flour would be the limiting reagent. Once it runs out, it limits the amount of cookies you're able to make, right? You can't make any more cookies because it's gone. So the limiting reagent is the reactant in the question that gets used up first. It will then limit or determine the amount of product we can make. So now how do we find the limiting reagent? There's more than one way to do this, but this is the way I taught you in my class. We have 5 grams of aluminum and 10 grams of iron oxide. Pick either one of those. It doesn't matter which. I'll start with the aluminum. So I've got 5.00 grams of aluminum. Now what am I going to do with this? We were told that with it there's 10 grams of iron oxide. So I know how many grams of iron oxide I have. What I'm going to do is take this grams of aluminum and I'm going to ask myself, how many grams of iron oxide did I really need to react with this? Right? So again, listen to that question. How many grams of iron oxide did I need to react with the 5 grams of aluminum? That is just a straightforward stoichiometry problem. So we can take the grams of aluminum and switch the grams to moles of aluminum. Then, using the balanced equation, we can switch moles of aluminum into moles of the iron oxide, the Fe3O4. But I was wondering how many grams of iron oxide, so my last multiplier, I'll get rid of the moles of iron oxide, and I'll switch that to grams of iron oxide. Now you might be wondering, why am I asking that? Just wait and you'll see in a moment why I asked that question. So using a periodic table, 1 mole of aluminum has a molar mass of 26.98 grams. The iron oxide from the balanced equation, 3 moles, will react with 8 moles of aluminum. And then the molar mass of the iron oxide, 1 mole, I'm going to calculate that with a periodic table. We have 3 irons and 4 oxygens, so 3 times 55.85, the molar mass of iron, plus 4 times 16, the molar mass of oxygen, 231.55 grams. I'm going to keep 3 digits in my answer. 3 digits divided by 4 and times by 5. The smallest number of digits was 3. So on my calculator, I'm going to start with the 5 grams. I'm going to divide by 26.98. I'm going to multiply by 3. And I'm going to divide by 8. And I'm going to multiply by 231.55 equals, keeping 3 digits, 16.1 grams of the iron oxide are needed. All right, so if you're going to use up 5 grams of aluminum, you need 16.1 grams of iron oxide. So why did I ask that? Well, we know that we have 10 grams of iron oxide. Okay, so we need 16.1, but we only have 10. Okay, so since we have only 10 grams of the iron oxide, that means we don't have enough iron oxide to use up the aluminum. The iron oxide will be used up. The reactant that gets used up is the limiting reagent. Therefore, iron oxide Fe3O4 is limiting. Okay? Now the other reactant, the other reagent, the aluminum, it's going to be left over. It would be in excess. Therefore, aluminum will be in excess. And all that means is at the end of the reaction, there's going to be some leftover aluminum metal. Now, I said a moment ago that it didn't matter which reactant you started that with. Let me just quickly show you what else you might have done. Suppose instead of saying you have 5 grams of aluminum, suppose somebody said that we have 10 grams of iron oxide. So 10.0 grams of Fe3O4. What they're going to do is say, if I have the 10 grams of iron oxide, they look here, they say, well, we know we also have 5 grams of aluminum. So they'll ask, how many grams of aluminum did I really need to react with this iron oxide? So how many grams of aluminum did I need? Because I know how many grams I have. And we're going to do the same kind of reasoning. So we'll switch our grams of iron oxide to moles of iron oxide. And then we'll switch the moles of iron oxide using the balanced equation to moles of aluminum. And then we'll switch the moles of aluminum to grams of aluminum. So the molar mass of the of the iron oxide we said was 231.55. From the balanced equation, 8 moles of aluminum will react with 3 moles of iron oxide, and 1 mole of aluminum weighs 26.98 grams. So on my calculator this time, I'll take 10, divide by 231.55, multiply by 8 and divide by 3, and times by 26.98 equals. I'm going to keep 3 digits again. 10.0 has 3 digits, and the molar masses have more than 3 digits, so we use the smaller number of digits, and we'll get 3.11 grams of aluminum are needed. What do I mean are needed? This is how much aluminum you would need if you're going to use up all of the iron oxide. Do we have this much aluminum? So we look back at the question and say, well, we actually had 5 grams of aluminum. So we have 5 grams of aluminum. But we needed only 3.11, which means we have more aluminum than we needed. So if we have more aluminum than we needed, then the aluminum is in excess. We have more than enough. It's in excess. If the aluminum is in excess, then the other reactant, therefore the iron oxide, is limiting. All right, notice that's the same conclusion that we reached when we started the question with the aluminum. We concluded there that the aluminum would be in excess and the iron oxide would be limiting. So we get the same result no matter which reactant you begin with. So why did we want to know what the limiting reactant was, the limiting reagent? Remember that in the example of baking cookies, when you ran out of flour, you couldn't make any more cookies. Even though you might have more butter, you might have more eggs or chocolate chips, it doesn't matter. The flour ran out, you have to stop baking. So how many cookies can you actually make? Well, it wouldn't depend on the eggs, it wouldn't depend on the butter, because you have a lot of that left over. The amount of cookies you could make would depend on the flour, because it ran out first, and you had to stop baking. So the reason we figure out the limiting reagent is so that when we want to know how much iron would be produced, we can now know that we're going to start that calculation not with the aluminum up here. We don't care about the 5 grams of aluminum. We're going to start with the 10 grams of iron oxide, because the iron oxide was our limiting reagent. So when you are calculating how many grams or how many moles of product can you make, you need to use the limiting reagent as your starting point. That's the key idea. Okay, so the whole reason for identifying the limiting reagent is because you must start with the limiting reagent to do any predictions about how much product would you make. So now we can switch the grams of iron oxide to moles of iron oxide. Using the balanced equation, we can switch moles of iron oxide to moles of iron metal, Fe, and then with the molar mass, we can switch moles of iron to grams of iron. All right, so the balanced equation ratio told me 9 moles of iron for every 3 moles of iron oxide. The molar mass of iron oxide, 1 mole, was 231.55 grams, and the molar mass of iron metal from a periodic table, 55.85 grams. On my calculator, we're going to keep 3 digits in the answer. So 10, I'll clear that so you can see, 10, and we're going to divide by 231.55, times by 9 and divide by 3, and times by 55.85. Keeping 3 digits, we get 7.24 grams of iron metal will be produced. Okay, so you identify the limiting reagent so that you can start with it when you're making any predictions about how much products you can make. What mass of excess reagent would remain? The excess reagent was the aluminum. So we're really asking how many grams of aluminum would remain. Well, to answer this could be a very quick subtraction, or we might need to do a unit multiplier followed by a subtraction. How do you know what to do? Well, in this particular question up above, when we identified the limiting reagent, we flipped a coin and said we'll start with the aluminum metal as our starting point, and we calculated how many grams of iron oxide we would need. Because we did it this way, we don't know how many grams of aluminum got used up. So I'm going to have to calculate that here with a string of unit multipliers. However, you remember we did that question up above a different way. If you had started the other question like this, 10 grams of iron oxide, we calculated earlier 3.11 grams of aluminum would react with that. So if we had set up like this in the earlier part B, we already know how many grams of aluminum would react. So now we just have to subtract it from the mass that we have to figure out how much is left over. Because we didn't start like that here, then we need to take our limiting reagent, 10.0 grams of iron oxide, and go tell me how many grams of aluminum would react with that. The aluminum is our excess reagent. So we'll switch the grams of iron oxide to moles of iron oxide. And this is the same thing we did a few minutes ago. We'll switch the moles of iron oxide to moles of aluminum, and then moles of aluminum to grams of aluminum. The balanced equation told us that 8 moles of aluminum for every 3 moles of iron oxide. The molar masses, 1 mole of iron oxide, 231.55 grams, and aluminum's molar mass, 1 mole is 26.98 grams. Grabbing a calculator and evaluating that, we should get 3.11 grams of aluminum are needed or will react. So we remember we had 5 grams of aluminum, but only 3.11 grams are reacting. So what mass is going to be left over? What mass will remain? So we take the amount that we had, 5 grams, and we subtract the amount that reacted, 3.11 grams, and we're going to get the amount that's left over. When you're subtracting measured numbers, you remember we round off our answer based on decimal places. So 2 decimal places here and 2 decimal places here. We're going to keep 2 decimals in this answer. So 5 take away 3.11 gives me 1.89 grams of aluminum will remain. Okay, so we found out how many grams, 3.11 grams of aluminum will react. And now by subtracting that from how much we started with, we get the mass that will remain. The part E, what mass of aluminum oxide would be produced? What mass of aluminum oxide would be produced? We look back at the balanced equation. Aluminum oxide was the other product. There's 2 ways to do this. In part E, we're going to do it with unit multipliers, and then part F, there is another way to do that without unit multipliers. So doing it the way we've done all the others, we're going to start with the limiting reagent, so 10.0 grams of iron oxide. And by now you should know what you're doing. Go calculate how many grams of aluminum oxide would be produced. So we need to switch the grams of iron oxide to moles of iron oxide. Using the balanced equation, we'll switch the moles of iron oxide to moles of aluminum oxide, and then the moles of aluminum oxide to grams of aluminum oxide. The first guy we've used several times. 1 mole is 231.55 grams. From the balanced equation, 4 moles of aluminum oxide for every 3 moles of iron oxide. So 4 moles of aluminum oxide for every 3 moles of iron oxide. And then the molar mass of aluminum oxide, periodic table, we have 2 aluminums, 2 times 26.98, and 3 oxygens, 3 times 16, 101.96 grams. I'm going to keep 3 digits in the answer. 10.0 has 3 digits, and these other numbers have more than 3 digits. So using the calculator again, here we go. So we have 10 divided by 231.55 times 4 and divided by 3, and then multiplied by 101.96 equals. Keeping 3 digits, we get 5.87 grams of aluminum oxide. All right. And the last question, calculate the mass of aluminum oxide produced, again, but this time without a unit multiplier. Well, how can we do that if we're not going to use a unit multiplier? I'm going to rely on a concept that some of us learn in grade 9 science. It's called the law of conservation of mass. During any chemical or physical reaction, mass does not change. So if you look back at our chemical reaction at the top of the page, I'm going to write some numbers underneath. We've already determined that 3.11 grams of aluminum would react, right? That was the answer in part D. 3.11 grams of aluminum were reacting. We know the iron oxide is completely reacting, and its mass was 10 grams. We already found that there would be 7.24 grams of iron metal being produced, and the question is, how many grams of aluminum oxide would also be produced? So if you realized that of the 4 things in the equation, we already know 3 of them, then we can find the 4th one by using just the law of conservation of mass. The total mass before the reaction was 10 plus 3.11. So 10 plus 3.11. This has to equal the total mass after the reaction. So 7.24 plus X. If I want to know this aluminum oxide, then I'll add these 2 numbers and subtract the 7.24. So subtract the 7.24, and we get 5.87 grams is left. So all I'm doing down here is saying 3.11 grams plus 10.0 grams, those were the reactants, minus the 7.24 grams, which was the one product that we knew. This would give me the mass of the remaining product, which was 5.87 grams. And if you take a look, that's the same answer we got using unit multipliers earlier. All right, so there's a multi-part question on reaction stoichiometry using limiting reagents. Again, the limiting reagent is the reactant that gets used up first in the chemical reaction. Once it's used up, the reaction stops. So when you're calculating how many grams or how many moles or how many liters of product you're going to make, you have to do that calculation starting with the unit multiplier in your unit multipliers. Sorry, starting with the limiting reagent, rather, in your unit multipliers. So I hope that helps. Good luck with your homework or with your studying.